Hello, now we are going to look at proving DeMoivres' theorem using induction. And DeMoivres' theorem is, again, our polar form of our complex numbers to a particular power of n, works out this way. DeMoivres' theorem, written as this, is on page 20 in our log tables. As an aside, writing this out in the exam, you can see the amount of space I've left myself here, gets very long and irritating to write. So you could write down in the exam, sine theta is just capital S of theta, cos theta is capital C of theta. Make sure you keep the brackets, don't just call them S and C, because you need to be able to deal with different angles than theta being part of your proof. But that can save you space and make it easier to write down. I am not going to do that here because I don't want to introduce capital C and capital S as a different looking thing to have written down on the page. I'm going to write it as sine and cosine, which we're more used to, in the hopes that that will make the steps easier to follow. But it is perfectly fine for you in the exam to write something like this down, and then you have slightly shorter line lengths to try and keep track of. So as with any proof by induction, we always start out with the same steps. Show that this relationship that we're trying to prove is true for a particular value of n. And our n is our powers here, or multiply here. And in this case, we want to show that it is true for n is equal to 1, because there's no other restrictions we have to worry about, so we start with n is equal to 1. So we write that down and we just do the substitution. This is the relationship we want to show, so we just put n is equal to 1, and I'll write that now. And we see that the left-hand side, we'll use this notation later, so we may as well write it down now. Left-hand side is equal to right-hand side. This is identical to what's on the other side. I should close that bracket there, and I should have a bracket there. So left-hand side is identical to right-hand side, so it's true for n is equal to 1. Where we have a power of 1, this is pretty trivially just true. Now we're going to do our second step for any proof by induction, which is to write down what this pattern should look like for a particular value of n, which we're going to call k. Say 1 would be a particular value of n, so k could be 1 or k could be 10, doesn't really matter. We're saying that we're going to assume that this is true. This relationship holds for a particular value of n, just like we picked the particular value of n being 1 for our first example here. So we're going to write down what this pattern looks like if it were to be true, or if we assume it to be true for n is k. So the only thing that I have done, as opposed to how we get the formula in the log tables, is I've put a k anywhere there was an n. So I am going to assume that this is true. Now, if we assume that this relationship holds for a particular value of n, k, which again could be 1 or it could be 2 or it could be 10, if it's true for a particular value of n, can we show that it must be true for the next value of n? So as a specific example, if we showed that this relationship must be true for n is equal to 1, like we did, can we show that in general it must also be true for n is equal to 2? Automatically, would we be able to show that if it's true for n is equal to 1, that it must be true for n is equal to 2? Because then it would also have to be true for n is equal to 3, and so on. So can we show in general that if this relationship is true, the n is equal to k situation is true, can we show that the next value of n must also be true? Does the pattern hold for the next value of n? And if we can show that, then we have done our proof. So what we need to start with is writing down what this should look like. So we already know what the n is equal to k situation looked like, we just wrote it down. What should it look like if the pattern held for n is equal to k plus 1? So let's write down what it ought to look like. So we haven't proved anything yet, but this is what the left-hand side should look like for the n is equal to k plus 1 situation. This is what the right-hand side should look like for the if n is equal to k plus 1 situation. All that's happened is anywhere there was an n, I have put in k plus 1. That's all. And this is what we should be able to get to. Can we start from what we have assumed to be true And using algebra and trigonometry, can we rearrange it to look like this? Can we show that if this relationship is true, without breaking any rules of maths, that this relationship must also be true? So what we're going to do is start from the n is equal to k situation and use some rules of algebra and trigonometry to try and rearrange it to look like this. There's one step I want to do, which is to show that this bit here is the same. If I multiply this bracket out, this is just theta outside of a bracket, so we should have k theta plus theta, and this is exactly the same. The angle inside the sine and the cosine should be k theta plus theta. That's just multiplying out those brackets. That's all I'm doing there, just to show what it is we're aiming for. So that's what we are trying to end up with. And as always, it is better to simplify what you are aiming for so it's easier to see when you've got there. This effectively has the common factor of theta taken out of it. If you want to think about it in algebraic terms, this is multiplied out and maybe easier to see when we're trying to do our proof. So always try and simplify your k+1 situation before you dive into the main part of the derivation. As an aside for the exam, this is at least half of the marks for the question. We have done basically no maths. We have simply remembered the steps for all proofs by induction. Show it's true for n is equal to 1. Assume it's true for n is equal to k. Show what it looks like for n is equal to k+1. That is usually more than half of the marks for the question, and we have done no maths yet. But we are about to. So we're going to write down the n is equal to k situation and try and derive this from it. Now, we're starting with the n is equal to k situation. How do we get to this? Well, if I look at the left-hand side, as I usually do for these questions, how would I go from here to here? Well, if I have n is equal to the power of k+1 of this thing in the brackets, so inside of this bracket, I am to the power of k+1. That means I have k of these things multiplied together, k of this big bracket multiplied together, times 1 of this bracket multiplied together. If I am adding the indices, I was multiplying these brackets together. So I have k of these brackets multiplied together times 1 of these brackets multiplied together. Well, I've already got k of these brackets multiplied together on the left-hand side. So how would I get the same left-hand side as I'm aiming for? Well, I would multiply by 1 of this bracket. I would multiply by or on cos theta plus I sine theta. You have the smallness of the writing. So this is to the power of 1. So if I multiply these two brackets together, I would have this bracket to the power of k+1. If I am multiplying these two brackets together, the same bases together, I add the powers and I'd end up to the power of k+1. But this is an equation, so I must do the same thing to the other side, to the right-hand side. I'll write that out. When we tidy this a little bit, I've rewritten this as I say, the left-hand side is now sorted. The left-hand side looks exactly the way it's supposed to, because I multiplied my two brackets together to the power of k and the power of 1. So I add the powers when I'm multiplying the same bases. So the left-hand side now looks as it's supposed to. I now have it looking like I want. I started with the kth situation. I am now at the k+1th situation without breaking any rules of maths. So the left-hand side is perfect. Can I make the right-hand side look like this? Can I rearrange this mess to make it look like this? So I have taken the radius parts. That should be power of 1, I suppose. And I have or to the k times or to the 1. So I can, exactly the same argument as with the brackets on the left-hand side, I can multiply the same base and I end up with or to the k+1. So this bit is fine. Now can I get all of this trigonometry to simplify to this? So let's just multiply out these brackets and see what we get. It'll be a bit messy, but let's see if we can identify anything that we can do with these brackets multiplied out. So now that I have the left-hand side as I want it, I'm not bothered to rewrite it because it just takes up space. So I'm purely dealing with the right-hand side and simplifying it. So all I'm doing is multiplying out these brackets, the same way as we've been multiplying out brackets for years. First thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket, or if you have a different way of multiplying out brackets, that's totally fine. We multiply this out, and now we're going to do a little bit of tidying. The first thing that jumps out at me here is I have I squared, which I know is -1, and I also have like terms. I have stuff involving I. Am I missing an I there? I am. That should be I. So I have stuff involving I. The two middle terms are imaginary. They share I, and I will have two real terms when I rewrite this as minus. So I'm going to group my real terms with group my real terms together, group my imaginary terms together, and then see if I can identify any trigonometry I can do to simplify it to make it look like this. Now I have grouped my real parts together and my imaginary parts together. I see I have cos multiplied by cos minus sine multiplied by sine. And that makes me think of my trigonometry identities that are on page 14 in my log tables. So I'm going to go and see if I have any identities that would allow me to simplify this, and any identities that will allow me to simplify this. When I find my substitutions, cos of a plus b is cos a cos b minus sine a sine b. This one's a little bit trickier to see because it's the wrong way around. So sine of a plus b is sine a e cos b, and I have the cos in front of the sine. But we know that the order of multiplication does not matter. So it doesn't matter that we rearrange the sine in front of the cos. It will work out the same way in both cases. So we can use these trigonometric identities on page 14 in the log tables to write down this fact here. And you can see the advantage in having simplified here. By the time we'd finished doing this in the exam, we could be quite tired, and it would be difficult perhaps to spot that you can take out the common factor. But because we did it up here, it's easier to see. So our final line then is to make the right-hand side look like the right-hand side over here. So the right-hand side is now correct, just like we had for the left-hand side. It looks like the k+1 situation. The right-hand side is now sorted. So what we did was start with the particular value of n, k, and we said if a particular value of n works, then the next value of n must also work. And this allows us to write down our conclusion. Our final block of marks is for our conclusion, and I'll write it out and talk about it. So our final statement, our final block of marks is as n is equal to k+1 situation is true if n is equal to k situation is true, and we showed that n is equal to 1 is true, it works. Therefore, the next value of n must work. So we showed that if n is equal to k is true, the next value of n must also be true. Well, that means that if n is equal to 1 is true, n is equal to 2 must be true. But if n is equal to 2 is true, if this pattern holds for n is 2, then it must also hold for the next one, which is n is 3, and so on. So we are able to build up to it working for any value of n from showing that it worked for a specific value of n, hence induction. Therefore, it must be true for all values of n element natural numbers. And that is what we need for the proof of DeMoivres' theorem via induction. And again, a reminder, up to here is more than half of the marks. And that's what we need for now.